Well, now we are in section 2, the paragraph type section. Let's look at the paragraph for questions 6 to 8. It says, in the figure, two spherical conductors of radii A and 2A are separated by a large distance. Initially, switch S1 is kept closed and S2 open. Now S1 is opened and S2 is closed at t equal to 0. And this is the network given to us. We have switch S1 here. There is a battery of EMF V. The switch S2 is here. Now question 6 says, current through resistance R as a function of time is. Well, the question involves concepts of current, electricity and also capacitors. So after switch S1 is open and S2 is closed, the circuit will look like this. Effectively, it's like this. The battery is disconnected, so it doesn't really matter. Now, let's say there is at time t after closing of switch, charge here is Q. That means Q charge has flown through resistance R and current at that instant is I. Here the charge is initial charge, say Q0 minus small q, because the charge will be conserved. And what's the value of Q0? Q0 is equal to capacitance of this into V, because it was initially charged to potential V, and its capacitance is, its radius is 2a, so its capacitance is 4 pi epsilon naught 2a into V. That means it is equal to 8 pi epsilon naught a into V. That's the value of Q0. And at an instant when S1 is disconnected and S2 is connected, this is the situation. Of course, the two spheres are far apart from each other. So at some time t, the equation will be Q0 minus Q by its capacitance, which is 8 pi epsilon naught a, minus R into I, which is dq by dt, equals the potential of the other sphere, which is equal to Q by 4 pi epsilon naught a. This gives us R into dq by dt is equal to, let us make a small substitution. Let's put 4 pi epsilon naught a at C. So 8 pi epsilon naught a becomes 2C, obviously. So R dq by dt is equal to Q0 minus Q by 2C minus Q by C, and which simplifies further. If I put it here as 2C, it is Q0 minus Q minus 2Q, that is, it is 3Q here. And if I do the cross multiplication, we get dq by Q0 minus 3Q equals dt by 2RC. We can integrate. Here it's 0 to t. And the value of Q is 0 initially, and let's say at time t it is Q. The left hand side gives us ln Q0 minus 3Q divided by minus 3. The limits are 0 to Q. And on the right hand side we have T upon 2RC. So we have now, if I substitute the values, we get ln Q0 minus 3Q divided by Q0 is equal to minus 3T upon 2RC, and this gives us the value of Q on further simplification as Q0 by 3 into 1 minus e to the power minus 3t upon 2RC. This is the expression for charge as a function of time t. The value of Q0 is already there. We have to find dq by dt. So current I will be equal to dq by dt and comes out to q0 by 3. The first term derivative will be 0. It is then minus into minus 3 by 2 RC. So that means it is 3 by 2 RC into e to the power minus 3t by 2 RC. If we substitute the values, the current comes out to be equal to V by R e to the power minus 3t by 8 pi epsilon naught 8 into R, which is matching with option D. So option D is correct. Let's go to the next question now. Question 7 says final charge on the sphere of radius A is. So we can find final charge on sphere A by using the exponential expression for small q in the previous question. So the final charge, if we put that as t tends to infinity, expression of q is q0 by 3. The q0 was 8 pi epsilon naught a v by 3. So that is matching with option B. We can also find charge on the sphere of radius A by simply conserving the charge and equating the potentials of the two. If we do that, we get q0 minus q. The potential of the first sphere will be q by c. That means q0 minus q by 8 pi epsilon naught a, and that is equal to q by 4 pi epsilon naught a, and this means q0 minus q is equal to 2q. So we again get the same thing, that small q is equal to q0 by 3, and we get this expression. So for question 7, answer is B. Let's go to the next question now. Question 8 says total heat dissipated through resistance R is. So what we will do here to find the total heat dissipated is, we take the initial electrostatic energy stored here and the final electrostatic energy stored in both these two. The loss in the electrostatic energy is equal to the heat dissipated through the resistance R. So heat dissipated H is equal to electrostatic energy initially minus electrostatic energy final. Now the value of Ui is equal to half the capacitance, which was 8 pi epsilon naught A into V square, and the final potential is q0 by 3, which is the charge here we just found out, and divided by its capacitance, which is 4 pi epsilon naught A. Let's put the value of q0. q0 was 8 pi epsilon naught A into V divided by 3 into 4 pi epsilon naught A. The final potential of both the spheres becomes 2V by 3. So UF will be half of the capacitance of the first capacitor, which is 8 pi epsilon naught A, plus the second capacitance, which is 4 pi epsilon naught A, into square of potential, which is 4V square by 9. And we use these two equations and also this equation. H is again Ui minus Uf, and if we perform the calculations, we find that the heat dissipated through resistance R equals 4 by 3 pi epsilon naught A into V square, which matches with option C. So option C is correct. Let's go to the next question now. Well, we now have the paragraph for questions 9 to 11. Let's read the paragraph. It says, the variation of temperature and pressure of the atmosphere with height h from the Earth's surface are given by T is equal to T naught minus beta h, and P is equal to P naught into 1 minus beta h by T naught, the whole thing raised to the power mg by r beta, where T naught is temperature at surface, which is 273 Kelvin. P naught is atmospheric pressure at surface. Beta is equal to 0.006 degrees C per meter. And capital M is the molar mass of air, which is about 29 gram per mole. It says take 0.82 raised to the power 5.7 as 0.32. Consider air to be a mixture of diatomic gases. Speed of sound in atmosphere at height h0 is 1080 km per hour. Well, with this information, question 9 says atmospheric temperature at height h0 is. We have to find the temperature, atmospheric temperature at height h0. Well, we have been given the speed of sound in atmosphere at height h0. We can use the expression for speed of sound in a gas, and that expression is V is equal to under root gamma RT by M. Okay, so let's try using the expression V is equal to under root gamma RT by capital M, where gamma is the adiabatic exponent, and for a diatomic gas the value of gamma will be 7 by 5 or 1.4. So since we have V and gamma is known, R is known, capital M is known, we can find T. So expression for T then becomes T is equal to V square M upon gamma R. Let's put the value of V. V is given as 1080 km per hour. So the value of V in SI units will be 1080 multiplied by 5 by 18. So that is equal to 300 meter per second. So temperature T turns out to be 300 square into M, which is 29 gram per mole. That means it is 29 into 10 to the power minus 3. Let's say it's 1.4, and value of R is 8.314 SI units. After performing this calculation, you will find the value of T turns out to be equal to about 224 Kelvin, which matches with option A. So option A is correct. Let's go to the next question now. Question 10 says value of height h0 is. We already have expression which relates temperature with height. The value of temperature at h0 is known, so we can find h using this equation. So the value of h is equal to T0 minus T divided by beta. We have the values of T0 and T. T0 is 273 Kelvin. It's given. T we just found is about 224 Kelvin. And the value of beta is 0.006. It is a degree C per meter. It can also be taken to be in Kelvin per meter. So the value of H comes out to be equal to 273 minus 224 is 49 divided by 6, and there will be 1000 here. This value, after calculating, you will find it's slightly more than 8000. In fact, it is close to 8170 meter, which is matching with option C. So option C is correct for question 10. Let's go to the next question now. Question 11 says atmospheric pressure at height h0 is. We can use this expression to find the pressure at height h0. Now that we have the values of P0, T0, beta, H, which we just found, H0 and mg upon R beta. So if we do this calculations, we are getting value of P is equal to P0. Options are in terms of P0 only, so we don't have to put the value of P0. We simply write P0 and then into 1 minus beta H, beta then H0 by T0, and raised to the power mg upon R beta. So what we do is we perform calculations of beta H by T0. Beta H by T0 value comes out to be equal to, it was 0.006 value of beta, and H was 8170 meter in the previous question. The value of T naught was 273 Kelvin, and this comes out to be equal to, well, on calculation you will find this value comes out to be about 0.18, and let's also evaluate the value of mg by r beta. So mg by r beta value comes out to, m is 29 into 10 to the power minus 3 SI units. Let's take value of G as 9.8 SI units. R is 8.31, and the value of beta is again 0.006. Again, calculations involved. This is equal to 29 into 9.8 divided by 8.31 into 6. And this value is very close to 5.7 on calculation. So the value of pressure P is P naught into 1 minus 0.18, which is 0.82, raised to the power 5.7. Now we have been instructed already to take 0.82 raised to the power 5.7 as 0.32. So this value is 0.32 times P naught. If we look at the options, it is matching with option C. So option C is correct. Let's go to the next question now.